Hello and welcome to what will be the last section out of Chapter 5, Section 5.3, which is Method of Partial Fractions. We've seen this a little bit with some of the problems that we did, but now we're going to kind of put it all together. So I just want to point out that for the stuff we're doing with Laplace, that kind of a big idea that I want you to get out of this, because, we are learning it in this way, and this isn't the way, I would have probably emphasized Heaviside a little bit more if we were in class. So for now, the big idea is really just solving differential equation with Laplace, okay? A little idea just to have you exposed to this in case you're doing differential equations for some other class down the line, is to just have an introduction to things like the Heaviside function, or you'll see it also called the unit step function, and what those transformations come to look like. So we're not going to focus so much as we would have in class when it comes to graphing things like that, but definitely knowing how to solve with Laplace is going to be a big thing. And so that's what we're going to do for this example. We are going to solve a differential equation like we would have solved in a previous unit, but we're going to do it using Laplace transforms. And so as we saw in yesterday's video, this means that we're going to take the Laplace of the whole thing, which translates to taking the Laplace of each individual piece. So we are taking the Laplace of y double prime minus 2 times the Laplace of y prime plus 10 times the Laplace of y. So again, pulling out any constants, any coefficients that aren't actually functions of what I'm assuming are t here. Okay, so referencing the table and just taking this a piece at a time, we'll go ahead and take the Laplace of y double prime, get s squared times capital Y of s minus s times y of 0 and then minus y prime of 0. That's what we get just for that. Now, this y prime of 0 is just 0, so I'll cross that out. Now we'll just focus on those other two terms instead. Okay, and then minus 2 times the Laplace of y prime, again referencing the table, that's s times y of s minus y of 0. Actually, with those initial values, I'm going to go ahead and plug in, this should be 2 right here and 2 right here, just to make it easier on the next step. And then plus 10 times the Laplace of y. This is just the definition here. If I take the Laplace of lowercase y of t, I get uppercase y of s. And then the Laplace of 0 is just 0, which I probably should have said right there. I just put a 0, so there you go. Okay, so I have some like terms that have a capital Y of s in them that I want to combine together, because remember, we're going to isolate that capital Y of s. So it looks like we have s squared, and then distributing here minus 2s, and here plus 10, that those are being multiplied by that y of s. And then my other terms that I get would be a minus 2s, a positive 4. All right, so isolating our capital Y of s, we get y of s is equal to a positive 2s minus 4 divided by s squared minus 2s plus 10. All right, so this is where we would have stopped yesterday, but what we want to look at from here is we want to solve our differential equation. That means we need to know what our solutions y of t look like. So this would be where we would get into our method of partial fractions, and we would look at splitting this bigger fraction up into smaller ones where we could actually look for a Laplace transform pair. We don't have a pair that matches with this, so we got to do a little bit of algebraic manipulation to get to that point. So what I'm going to do with the denominator here is just start by completing the square. All right, we have s squared minus 2s, We're going to bring that plus 10 out, and we're going to go ahead and complete the square here with the quadratic part and get a plus 1 that we negate with the minus 1. So that way we can factor this into s minus 1 squared plus 9. This is nice because if we look at the format that we have here, we would have s minus some alpha value. So we do have a shift in our transform function, our transform domain. And then this plus 9 is a perfect square, which means that this is probably omega squared. So when I go back and I look at the numerator here, this 2s minus 4, that doesn't really fit with this s minus 1 that we have right here. And in fact, if I try to just factor out and do 2 as my greatest common factor, this s minus 2 still doesn't really match. So we want the shift in the transform to match. And for that, that's where some of this algebraic manipulation comes in. We're going to just call this s an s minus 1, and then we're just going to negate what we did right there. So I have my minus 4 still on the outside. I changed my s into an s minus 1. What that does is add a negative 2 to this whole expression. So I'm going to negate that with a positive 2. So just checking my algebra here, 2s minus 2, and then minus 4 plus 2 would negate the minus 2 and the positive 2. So that works out. Okay. All right. So a lot of algebraic stuff going on there, but what that means is y of s looks like in the numerator 2 times s minus 1 minus 2 over s minus 1 squared plus 9. Now, if we would have had a nice denominator that factored, you could do a more traditional method of partial fractions. We did not have a nice one that factored here because our 10 is positive. If it would have been negative, that would have been a lot nicer. And we could have looked at doing some just traditional method of partial fractions. But this is another way in which we can split up our capital Y of s into two fractions that would give us a transform pair. And so that first numerator over s minus 1 squared plus 9, and then our second over s minus 1 squared plus 9. So I always need to review because it's easy to flip-flop these, but this is why you have your table to reference, is if we take the sine of omega t and we do the Laplace transform, we get, I'm referencing my table right now, we get omega over s squared plus omega squared. Okay. And then if we take the Laplace of cosine of omega t, that we get s over s squared plus omega squared. All right. Let me know if that's incorrect. I am going off the Laplace transform table here, and I'm pretty sure that's what we're getting. So, like I say, I always have to double check those. So cosine is the one where we get our function of s in the numerator. Okay, so that's going to be this first fraction that we have right here. Now it is shifted. So in that case, alpha is equal to 1. We shift it to the right 1, but it looks like based off of this, omega is equal to 3. And then over here, we have our sine. This is going to go to this is going to go to sine because we have a constant. Now this is not omega in the numerator. Omega is still equal to 3, and same thing happened here. So still a little bit more manipulation that we have to do with this. I'm going to go ahead and take the first one here. We have this constant of 2 that's not very helpful because it's not omega. But if I take the Laplace or the inverse Laplace of s minus 1 over s minus 1 squared plus 9, okay, then I'm just going to do that shift to the transform, and it looks like I have omega. So this one is actually not too bad. We just, that shift becomes an e to the t. So this is going to be 2 times e to the t times cosine of 3t And hopefully, and I kind of rambled a bit in the middle, but hopefully you can see where all those pieces came from there. So that's at least the first part of y of t. Once we perform that inverse Laplace, we are getting our solution here, lowercase y of t. Okay. And then this last one is tricky because we do still have this constant of 2, but for this transform, because it says that we have omega in the numerator, we're going to have to, again, do a little, manipulation here. And we're going to say, okay, if I multiply by 3 in the numerator to get that omega value, then I at least just have to do the same in the denominator. Okay, so what we're going to do for this is, remember we had the minus sign between them. We're going to pull out that constant of 2. This 3 that we had to multiply in the denominator, we are also going to pull out because that doesn't match our form of our inverse Laplace here. Okay, so if I do the 2/3 out in front, that gives me the ability to have the 3 in the numerator, and then I have s minus 1 squared plus 9 in the denominator. And then that does fully fit the form here of doing sine of omega t. So this is going to be minus 2/3. I still have this shift, alpha is still equal to 1, so I still have an e to the t, and then this will be a sine of 3t. And that's the other piece of my function of y here. So that is my final solution right there. And again, this is kind of putting everything all together that we've done. As you can see, we use Laplace transform pairs. We used an initial Laplace, and then we took the inverse, and then we also have used a little bit of partial fractions, and we put that together with how we solve our differential equations. And so hopefully that was a good example for you to just get started on the problems that you're going to see in the assignment. Good luck. Please let me know if you have any questions with that.